Hello and welcome to everyone. Today we are going to discuss about design of rigid pavement. This is design. In this design we will discuss some important criteria or the parameters for designing a rigid pavement. Now let us see some points here. Design of rigid pavement is based on Westergaard's analysis. Now, Westergaard is considered as a pioneer in providing the racial approach to analysis of stresses in rigid pavements. Now, here for design of rigid pavement, two types of stresses are considered, namely wheel load stresses and temperature stresses. In Westergaard's analysis, he took two types of stresses, which is namely wheel load stresses. These are due to the number of stresses which are being imparted by the various wheel load, and another one is temperature stresses. Now in wheel load stresses, it is due to the loading of the various vehicles which is transferred through the wheels of particular vehicle. And temperature stress is something which can be considered in daytime and nighttime also, due to change in temperature in between the various layers of the rigid pavement, or the difference due to the difference in temperature, there will be some stresses developed in the rigid pavement. And it may also be seasonal, where due to different seasons and the temperature variations, due to that it will occur some stresses. Now temperature stresses can also impart to this frictional stresses in seasonal cases. Also, we need to know what are the loading conditions in order to find the nature of these stresses. Now we have to have an idea how and where the loading is occurring on the surface of a rigid pavement. So we have to categorize in which area the loading is going to happen. Now let us see another point. We will consider different design parameters using which we will find the stresses values. Now for finding out the stresses value, we need certain parameters. Now what are those parameters? The first one is, some of the design parameters that we are going to discuss is modulus of subgrade reaction. This is a value of the modulus which we have to find out by plate load test. We will see that one in the next discussion. Then radius of relative stiffness we have to know. Then another parameter is radius of wheel load distribution. Now, and the other one is equivalent radius of resisting section. Let us see the first one and try to understand what is modulus of subgrade reaction. Modulus of subgrade reaction. Modulus of subgrade reaction may be defined as the pressure sustained per unit deformation of subgrade of specified deformation or pressure level using specified plate size. Modulus of subgrade is usually found out by conducting plate load test, in which we will see for a certain pressure level or specified what will be the specified deformation, and we will try to calculate the modulus of subgrade reaction using some formula that we will discuss later. Now in Westergaard's analysis of stresses in rigid pavement, he considered a pavement to be a thin elastic plate resisting on soil subgrade. In Westergaard analysis of stresses, what he did was, he considered the pavement to be behaving in such a way that it is a thin elastic plate. Now it is something like it will behave in an elastic manner, and also he considered that the soil subgrade is to be a dense liquid. Now in his analysis he assumed that the subgrade provides an upward reaction P which is directly proportional to deflection delta. In his analysis, what he did and what he assumed was that the upward reaction which is given by the subgrade, that is denoted by small p, is directly proportional to the deflection of the slab delta. That is, p is directly proportional to delta, or we can also say that p by delta is equals to a constant which is k. Now K is our modulus of subgrade reaction, where K is defined as modulus of subgrade reaction, which is expressed in kilogram per centimeter cube and is given by a pressure in kg per centimeter square per centimeter deflection. Now P, the unit of P should be in kilogram per centimeter square. For determining the value of K, the displacement value of delta is taken as 0.125. Now here what we will do is we will conduct a plate load test in which the deflection amount or the displacement value is taken as 0.1275. If P is the pressure sustained in kg per centimeter square by the rigid plate of diameter 75 centimeter at a deflection delta equals to 0.125 centimeter, the modulus of subgrade reaction is given by, now what will be the value of the modulus of subgrade reaction K? We will see in an equation, that is K is equals to P by delta. Now if we substitute the value of delta 0.125, it will give us the exact value, where we can find out by putting the value of the pressure and dividing it by 0.125, which is the deflection delta when we use a rigid plate of 75 centimeter plate. Then it will give us the value of modulus of subgrade reaction K. Now let us see what is radius of relative stiffness. Now the subgrade offers a certain degree of resistance to the slab deflection. Whenever the slab on the slab there is a loading, the slab will tend to deflect. That deflection is prevented by some kind of resistance which is offered by subgrade, and we will see how much it is going to resist. The subgrade deformation is same as the slab deflection. Now what he considered was the deformation in the subgrade, which is due to the deflection of the pavement. Both are same. Now what amount of deflection is occurring, that amount of deformation is going to happen in the subgrade. However, the tendency of the slab to deflect is dependent upon its flexural strength, which depends on its thickness and the strength characteristics of the pavement. Now the tendency of the slab to deflect is dependent upon the flexural strength of the pavement, and the flexural strength is again dependent upon the thickness and the strength characteristics of the slab pavement slab. Now the relative stiffness of the slab with respect to the subgrade support is dependent upon the properties of the slab and the pressure deformation characteristics of the slab materials. Now the relative stiffness, how much stiffness it's going to offer by the of the slab with respect to the subgrade support, is again dependent upon the properties of the slab and the pressure deformation characteristics of the slab material, subgrade material. Now the subgrade is usually due to the it is made up of the our usually occurring soil. Now the soil particles will be having certain deformation characteristics, and also the pressure distribution will be slightly different as compared to your slab properties. Now if we combine both of them, then the relative stiffness of the slab will be due to this both combination. The radius of stiffness, the slab deflection is measurement of the magnitude of the subgrade pressure. Now we have also defined it already, we have discussed this point, that the deflection of the slab is a direct measurement of the magnitude of this subgrade pressure, how much pressure it is offering by the subgrade or occurring in the subgrade. It is a direct measurement of the slab deflection. The pressure deformation characteristics of rigid pavement led Westergaard to define the term radius of relative stiffness L in centimeters is given by the equation. Now Westergaard is going to define a term which is called radius of relative stiffness. Why he is doing that is in order to let us find out the pressure deformation characteristics of the rigid pavement. Now he has given a term called radius of relative stiffness, which is denoted by small l, and he has given an equation for that. This is the equation, that is L equals to EH cube divided by 12k 1 minus mu square to the power 1 by 4. Here E is your modulus of elasticity of the slab, H is your slab thickness, E is your modulus of elasticity of cement concrete. Then Poisson's ratio is for the concrete is 0.15, that is the value of mu, and the capital K is your modulus of subgrade reaction, which we have already discussed earlier. Now relative stiffness. Westergaard expressed equations for determination of stresses in rigid pavement. Now Westergaard has used all the values of your modulus of subgrade reaction and the radius of relative stiffness in order to find out the stresses in the rigid pavement. So using all these properties, we can determine the stresses in our rigid pavement. So what are all those properties? The first one is modulus of subgrade reaction K, which we have already discussed. Then another one is radius of relative stiffness L, which we have discussed just now. And the other one is equivalent radius of resisting section B. So this is a new term which we will discuss later. Let us see what is radius of relative stiffness by solving a problem. Calculate the relative stiffness of 15 centimeter thick cement concrete slab using the following data. Now he has given in the question the slab thickness is given and some data is given, and using which we have to find out the radius of relative stiffness, that is denoted by small l. Now modulus of elasticity of the cement concrete is given as 2.1 into 10 to the power 5 kg per centimeter square. Poisson's ratio of concrete is given as 0.15. Then the modulus of subgrade reaction K is equals to, now he has given K in the value of K the two values of K he has given. So for the different values of K, that is 3.3 kg per centimeter cube and 7.5 kg per centimeter cube, we have to find out the value of radius of relative stiffness. So the given data is slab thickness H is equals to 15 centimeter, modulus of elasticity of cement concrete, that is E equals to 2.1 into 10 to the power 5, then boson ratio is 0.15. Now for the value of K equals to 3 kg per centimeter cube, the value of radius of relative stiffness, that is L, is equals to, given by this formula, EH cube divided by 12K1 minus mu square whole to the power 1 by 4. You just substitute the value of E, H, K and mu. We will get a value of relative stiffness, radius of relative stiffness as 67 centimeters. For the value of 7.5, K value of 7.5, we will repeat the same process in which we will use this formula and we will substitute the values. Now all the values are same, however the value of K is changing as 7.5 now here. So just substitute all the values and calculate it. You will get a value of 53.3 centimeter, which is the final value of radius of relative stiffness. Now what we get from this problem is the influence of modulus of subgrade reaction on radius of relative stiffness of the slab is relatively small. Now the value of the modulus of subgrade reaction, that is K, the K value, does not have much of an influence to the value of radius of relative stiffness of the slab. Now up to this top portion we have understood the modulus of subgrade reaction and the radius of relative stiffness. Now let's move on to the next topic, that is critical positions of loading. The pavement slab has infinite length and width. Due to this region, the character or the intensity of maximum stress induced by the application of given traffic load is dependent upon the location of the load on the pavement surface. So now the pavement slab will be continuous and it will have infinite length, and the width of the pavement is also infinite, or it is big. So now due to this region, what happens is the stress induced, or the maximum stress induced, the intensity of the maximum stress is dependent upon the application positions of the application of the traffic load. So where a particular loading or location of the loading is occurring on the pavement surface, on that particular thing it is dependent that the maximum stress, we need to know the location of the loading in order to find out the maximum stress. So let us see a pavement in pictorial presentation of the representation of the pavement portion, in which we will try to locate what are the different types of loading position. Now there are three typical locations, namely the interior, the edge and the corner, where differing conditions of slab continuity exist. Now in the slab there are few portions where the loading positions will be critical. One is our interior, other one is edge and the corner. So all these three positions have different conditions of slab continuity. Now let us see that where are these interior, edge and the corner positions in a pictorial representation. Let us see, this is a portion of a rigid pavement. Now where will be our interior? The interior location will be somewhere here in the middle, and on the edge this will be our edge position for our loading condition. Then in the corner will be somewhere here. So these are the critical positions of loading which is to be considered in order to know the character or the intensity of the maximum stress induced by the application of traffic load. After knowing this critical position, we will move on to the next topic, These locations are termed as critical load positions. We already discussed that one. Now let's move on to the next. That is radius of wheel load distribution. Now whenever we are loading, load is occurring in on the pavement surface, what will be the condition of the loading we will try to understand what is the nature. Now the contact area of the wheel load is considered to be circular, though it is not actually circular. However, for the comfortably for analysis, we are considering the contact area due to the wheel on the rigid pavement as circular. Let us say this is a cross section of rigid pavement. This is our wheel. Due to this wheel loading, how the contact area will come up is something like in a circular manner. Now let's see that in a plan. Let us say this is the plan of a particular portion of rigid pavement. Now the contact area will be somewhat like this, which will be in circular format. The contact area A is given by the formula pi a square p, where A is the radius of the equivalent circular area of contact, then that is the radius of this particular circular section, then P is the contact pressure, how much pressure it is imparting. The wheel load of circular contact area may be expressed in terms of any of the parameters. That is, it can be either in terms of capital P, small p, capital A, small a and capital A. Capital A will be our wheel load. Capital A will be our wheel load, then small p will be our contact pressure. Small a is the radius of the equivalent circular area of contact. Capital A is our area of contact. Now the radius of wheel load can also be calculated as the radius is equals to root over capital P divided by small p, which is the pressure, into pi. Now equivalent radius of resisting section. What does it means? We will try to understand. We have already discussed about the critical load positions, in which we had interior loading position, edge loading position and corner loading position. When we consider the interior part of loading, the maximum bending moment occurs at the loaded area and acts radially in all directions. Now when we consider the interior part of the loading, that is somewhere in the middle of the section that we have just seen, the maximum bending moment is going to occur there at the loaded area, and it will act in a radial manner and in all directions. Now with the load concentration on the small area of the pavement, here is a question that arises as to what sectional area of the pavement is effective in resisting the bending moment. Now the load is concentrated on the small part, that is the interior part, small area of the pavement. Now the question is arising that up to what extent or up to what sectional area of the pavement it is going to effectively resist the bending moment. The interior point is loaded, only a small area of the pavement is resisting the bending moment of the plate. Then according to Westergaard, the equivalent radius of resisting section is approximated in terms of radius of wheel load distribution A and slab thickness. Now according to Westergaard, the equivalent radius of resisting section is found out by using two terms, that is radius of wheel load distribution denoted by small a and the slab thickness small h, and it has given a formula. that is small b equals to root over 1.6 a square plus h square minus 0.675 times of h, where a is your radius of wheel load distribution, h is your slab thickness in centimeters, b is the equivalent radius of resisting section. Now this formula holds true for a value of a less than 1.724 times of h. Then small a is our radius of wheel load distribution, again it is in centimeters. Then the slab thickness is in centimeter. If what will happen if the value of a is greater than 1.724 times of h, the value of b will be equals to a. Now the value of b is equals to a when the a value is 1.724 times h. A value is greater than 1.724 h. Let us try to solve a problem to find out the equivalent radius of section. Compute the equivalent radius of resisting section of 20 cm thick slab given that the radius of contact area wheel load is 15. Here the slab thickness h is given and also the radius of wheel load is also given, that is 15 cm. Slab thickness h is 20 cm, radius of wheel load distribution a is 15 cm. Now we have the formula which is given by b equals to root over 1.6 a square plus h square minus 0.675 when a is less than 1.724 h. Now let us see whether this condition is true or not. A by h, 15 by 20, so 15 by 20 comes up to be equals to 0.75, which is less than 1.74. Hence we can use the formula for finding b. So just substitute the value of a and h in the formula like this, and we will get a value of 14.07, which is the value of our equivalent radius of resisting section. Now this comes to the end of this video lecture. Now we will try to see some more topics in design of rigid pavement in next video. Probably we will discuss about various types of stresses, the temperature stress or some other frictional stress also. Thank you everyone.